In this lecture, we'll talk a bit more about how astronomers are able to characterize exoplanets. One of the goals of the Kepler mission is to find Earth-like planets that may be suitable for life. This is by no means an easy task, but astronomers have developed techniques to help us learn about these alien worlds. You may recall that depending on the technique used, we can get at properties like orbital period, distance, shape of orbit, planet size, and planet mass. Astronomers also have ways to estimate the density of exoplanets, and they can even learn about their atmospheres and temperatures. The radial velocity or Doppler technique can provide us with a minimum mass for the planet, as well as the eccentricity of the planet's orbit. The transit method can provide us with the physical size of the planet and the distance from its star. By combining these methods, we can determine the density of the exoplanet. This allows us to know what the planet is like, whether it's rocky like Earth or gaseous like Jupiter. The density of an object is its mass per volume. The Doppler method can give us planet mass. The transit technique can give us planet size, or the planet's radius. From the radius, we can calculate the volume of the planet. With data from both Doppler and transit methods, we can get density. The first exoplanet for which astronomers could calculate a density for was planet HD 20948b. Because the system is seen edge-on from our perspective, the Doppler method yielded a true mass and not just a minimum mass for the planet. Combining Doppler and transit data, astronomers calculated a density of 0.37 grams per cubic centimeter. This is less than the least dense planet in our own solar system, Saturn. On the other extreme is exoplanet Kepler 10c. This planet has a density of 7.1 grams per cubic centimeter, which is greater than that of Earth. Spectroscopy can reveal details about an exoplanet's atmosphere. When the planet moves in front of the star, it's like its atmosphere is in front of a hot light bulb. Absorption lines from the planet's atmosphere will show up in the spectrum, and we can therefore determine what elements are in the planet's atmosphere. This is the infrared spectrum of the planet HD 189733b taken by the Spitzer Space Telescope. It's useful to do spectroscopy in the infrared because that is where many interesting molecules, like those in greenhouse gases, have absorption lines. For HD 189733b, astronomers have solid evidence for significant amounts of water vapor in the planet's atmosphere. Follow-up observations made using the Hubble Space Telescope confirm the presence of water vapor, neutral oxygen, and methane. The Very Large Telescope has also found evidence of carbon monoxide. Systems that allow us to see transits also can give us information on a planet's temperature. When the star and planet are next to each other like this, we see the radiation from both star and planet. When the planet goes behind the star, we see only the star's radiation. If we subtract the star's radiation from our measurement of both planet and star, we have only the radiation from the planet. In some cases, astronomers can measure changes in the total brightness of a system as the planet orbits the star. From our perspective, we can see the planet undergo phases, much like the phases we see of Venus. Kepler has been able to measure changes in the light as the planet HD 189733b goes from new to crescent to gibbous to full and back again. With this data, we can make a temperature map of the planet's surface. This is a global temperature map of HD 189733b from the Spitzer Space Telescope. Hotter temperatures are represented in brighter colors. This planet is a hot Jupiter, and these types of planets are thought to be tidally locked to their stars, just as our moon is to Earth. This means that one side of a hot Jupiter always faces its star. As predicted, the map reveals that HD 189733b has a warm spot on its sunlit side, which is always pointed toward the star. The number of known extrasolar planets for which we have measured many key properties is now large enough that we are beginning to gain insight in how these planets compare to our own solar system. Some of the observations have been quite surprising. Let's first consider orbital distance. This is a plot showing a graph of exoplanet mass versus average orbital distance. There are many exoplanets that are much closer to their parent star than any planet in the solar system is to the Sun, and there are also some that are much farther from their star. Most exoplanets that have been discovered are within a couple of AU from their parent stars. This is because the Doppler and transit methods require observations of several orbits to confirm that the planet exists, and there has only been enough time since these methods were first used to look at systems where the planet is close to the star. Now let's consider eccentricity. All the planets of the solar system, except for Mercury, have orbits with low eccentricity, and most exoplanets with orbital periods of 20 days or less also have near-circular orbits. But the giant planets with longer orbital periods are different. Their orbits are, in general, quite eccentric. There is no observational bias towards more eccentric orbits for these stars. Therefore, the elliptical orbits for giant planets is a puzzle. Current theories of planetary formation suggest planets should form with more circular orbits. Finally, let's look at planet size. Prior to recent results from the Kepler spacecraft, most confirmed planets were gas giants comparable in size to Jupiter or larger because they are most easily detected. However, the planets detected by Kepler are mostly between the size of Neptune and the size of Earth. There is a general trend toward smaller planets being more abundant than larger planets. The trend likely continues to even smaller worlds, but we cannot be sure because such small worlds are at the limit of Kepler's measurement sensitivity. The actual number of small worlds is probably much larger. I've only covered a small piece of our ongoing quest to characterize exoplanets. I hope I've made you curious enough to explore a bit on your own. Take care. I will talk to you again soon.